So for this problem, to calculate the average velocities to help us estimate the instantaneous velocities at 1.5 and 2, I'm going to pick points that are right around 1.5. So I'm going to go between like 1.5 and 1.6, 1.5 and 1.51, so a little bit closer, a really small interval, 1.49 and 1.5, and 1.4 and 1.5. So I'm picking values on both sides like we did earlier. Same thing with between 2 and 2.1. So I'm going to show you how we can do this quickly with the graphing calculator because these do take a while. So when I go to put this in, I'm going to do this first one. I'm going to use my function which I have up there, and I'm going to open a set of parentheses for the numerator and then a set of parentheses for my first point. So 64 minus 16 times, now I'm going to put in my first point, so I might do 1.6 minus 1 squared. So that is my S of 1.6 minus now my S of 1.5. 64 minus 16 times 1.5 minus, I might have said S of 1.4, sorry, S of 1.5 if I screwed that up, 1 squared. Now this parenthesis closes S of 1.5, this parenthesis closes my numerator, divided by 1.6 minus 1.5. Calculate, and I get negative 17.6. Now, the reason that this helps us out is watch what we can do. I'm going to go down here and hit second entry, and it brings up what I just put in. Now if I want to do, say, between 1.5 and 1.51, I just need to change the 1.6 to a 1.51. So second, now I do need to insert the 1. I'll overwrite the 6 and insert the 1, and boom, I've already got it. So negative 16.16. So I'll let you guys try that on these other ones, and I'm just going to fill them in. Equals negative 15.84 on the intervals I happen to choose, equals negative 14.4. So remember, we want to get the instantaneous velocity, we'll call it IV, at 1.5. Well, look at what's happening. As we get closer from the right side, the numbers are getting closer to negative 16. As we get closer from the left side, they're getting closer to negative 16. So right in here is where that instantaneous velocity is going to lie, and we're going to estimate it at about negative 16. And it's a velocity, and remember what we're dealing with, negative 16 feet per second is our estimated velocity of that ball at that moment. Similarly, we could find all these values for the average value, getting closer and closer to doing it exactly at 2. So I went ahead and did these, and we get negative 33.6, negative 32.16. You probably already see where this is going. Negative 31.84, and finally negative 30.4. So we're doing average rates of change to help us estimate an instantaneous rate of change. So the instantaneous velocity at 2 is going to be, we look at right in between here, what would be right in between those? Looks like they're both converging to negative 32 feet per second. We're going to see with calculus how we can compute those exactly a little bit later this semester. Now, which one is greater? Well, it depends on what we mean by greater. The larger rate of change is negative 16 feet per second because negative 16 is a larger number than negative 32. Now, which one has the greater speed or greater magnitude? Well, that's negative 32 feet per second. If we take a look at our graph to see what's going on, we found the instantaneous rate of change at 1.5, and we found the instantaneous rate of change at 2. Well, the speed is going to be greater at 2 seconds because the ball is falling faster due to gravity. So when we talk about this more, we also found the slope of that tangent line. When we found the instantaneous rate of change, or instantaneous velocity at 1.5, we found the slope of this tangent line. So just like average rate of change finds slope of a secant line, instantaneous rate of change finds slope of a tangent line.